Swayam Prabha. Digital India. Educated India.
In our previous class we derived the governing equations for the thin film coupled with the boundary conditions. So, we will summarize those today and then proceed with a illustrative example of how to solve the thin film equations. So, the basic equations that we solved or that we derived are the continuity equation, the x momentum equation and the y momentum equation, which are given in the slide. Then the boundary conditions at the solid boundary, at the interface between the solid and the fluid you have no slip, no penetration boundary condition, and at the interface kinematic boundary condition, the shear force balance and normal force balance. Then we assume the variation of the surface tension of a particular form and also introduce the concept of disjoining pressure, so that we could write the pressure jump across the interface in terms of these parameters. I mean, these we did in significant detail, so I am just summarizing. Now based on various forcing parameters we ascertained various velocity scales. So, like for example, if surface tension gradient is dominant, then what is the velocity scale? If the normal pressure gradient is pressure difference is dominant, then what is the velocity scale? If the excess pressure is dominant, then what is the velocity scale? All these if the x body force is dominant, what is the velocity scale? If the y body force is dominant, what is the velocity scale? Now in the previous lecture we outlined a method of solution of these equations. See, these equations are strongly coupled and the nature is non-linear, and however it is possible to derive a single expression of H as a I mean single expression of governing differential equation, not expression for H directly, but governing differential equation for H as a function of x and time. So that we outlined, and the procedure is something like this. We started with the y momentum equation, then used the normal stress related boundary condition, then we calculated the axial pressure gradient, used the x momentum equation, integrated the velocity profile twice and have used the no slip boundary condition at the wall and the tangential stress related condition, and that u we finally substituted in the continuity equation, where we use the Leibniz rule to bring the ddx out of the integral, and in the process we use the kinematic boundary condition. So that eventually led to the equation number 30, which is the form with which we will start today, that del h del t plus del x of 0 to h u0 dy equal to 0. Starting from here we will go to the board and try to work out a simple problem. I will write the expression of u0 what we derived in the previous class, and we will start from there. So you have del h del t plus del x of u0 dy is equal to 0. u0 is equal to a into y square by 2 minus yh then plus epsilon beta by capillary number del tilde sigma y, where the expression for A we will write A is equal to del x of epsilon cube LC square rho g cos theta by mu UC H plus PS minus epsilon square LC rho g sin theta by mu UC. So, integral of u0 dy we can calculate, we will calculate it for a special problem, and then we will substitute that integral here. So, once that integral is substituted here, you will get a governing equation which contains h as a function of x and t, where are so this h I am not writing all the time that h is a function of x and t. Here you have h as a function of x and t. This term when integrated, these two terms, you will have h as a function of x and t. Even within A you have parameter h which is a function of x and t. Even PS has a dependence of h as a function of x and t. So, I mean the entire equation is flooded with the parameter h which is a function of x and t. So, we will define a problem. For problem definition and schematic I will refer to the slide, but I will work out the problem in the board rather than using the slide. So, example 1, gravitational spreading of a cylindrical drop. Okay, this is a very classical problem. Consider the drop shown in the schematic with that blue color. It is of cylindrical shape, that is along the z axis the length is very large. So, it is an infinitely long cylindrical drop, so to say. So, the z axis is not important, because it is infinitely long along the z axis, all the gradients along the z axis are not important. So, eventually whatever is happening in the xy plane is what is important. This drop is spreading due to gravitational forces acting on it, that is the situation that we want to mimic. This type of spreading is known as gravitational spreading. What is our objective? Our objective is to find out the height of the drop as a function of t and x. We would also find out the radius of the drop Lt as a function of time. It can be assumed that we are only interested at a time which is long after the drop begins spreading. Why? Because initially when the drop starts spreading, the inertia force may be important, and in the thin film analysis that we have made, remember that you can make thin film analysis even with inclusion of inertia force, but the analysis of thin film, the special type of thin film analysis that we have made, we have not, and that is the traditional thin film analysis, and that is the classical thin film analysis, that by utilizing the ratio of the length scales we have trivially neglected the inertial forces. But you can see that when the droplet spreads, it is I mean you cannot say, see you cannot always say that h is much less than L, and that is why during the initial stages the inertial effects may be important. Now, however, during the later stages when the droplet is almost towards the completion of the spreading process, then the height will become small and the length will become large. So, then the low inertia limit will work better. So, we will assume that at the time of our investigation the height of the film is much smaller than its radius, so that the thin film assumptions can be applied. Finally, we would also assume that the effect of capillary forces are negligible. I mean it is just for demonstrating a problem. I can that is what I intend to tell you, because if you include the effect of capillary force, I mean the same thing, but equations will become, sometimes equations may become intractable so far as what we can do in the scope of a class coursework, but I mean inclusion of surface tension forces, surface tension gradients, disjoining pressures, these are some of the very standard things that we commonly do in research, and even in may not be in research, even in advanced text, that is what is commonly used. But just purely to demonstrate you that how to solve the thin film equation, I will consider that the gravity is the dominating parameter. So as we have mentioned in the problem statement, we are only interested in a time which is long after the drop starts to spread. Clearly the drop starts to spread from an initial shape which is unknown. See, this problem, setting up the length scale is very challenging, because the droplet is, its dimensions are continuously evolving. You do not have a fixed L, you do not have a fixed H, and these are continuously changing. After sufficiently long time, there is no memory in the drop of its initial shape. The droplet has lost its memory that what was its initial shape completely. We are interested in precisely this time frame, that is the physics that we are interested to capture. Looking at the gravitational forces in the thin film equation, we find that these forces are proportional to sin theta and cos theta. Here theta is 0 because the plane is horizontal and gravity is vertically downwards. So here theta is 0 and only active component of gravity is the cos theta component, right. So that means, so basically G, in the y momentum G is acting, right. So the main reason, this is the main dominant force here, and this force is the main reason for the drop to spread. So we have our velocity scale from the y momentum body force, right, because the y momentum, in the y momentum there is a body force which is proportional to g cos theta, and here theta is 0, right. So because the gravity is vertically downwards, that is where the y axis is, that is how the y axis is aligned. That means that your UC will be decided by the body force in the y momentum equation. See, this is the first thing that you have to decide, what will be your scale. So that is the first point. Second point, we can easily infer that the radius of the drop will keep on changing with time and the height will keep on getting shorter, right. This is obvious, height will decrease, radius will increase because volume has to be conserved. We note that in this problem there is no natural time scale to speak of, that is why we cannot speak of any natural length scales also, because the length scales along x and y directions will keep on changing forever. Thus one can conclude that in the present case, in absence of any natural scales, we are likely to have a similarity solution. So I will show you that what kind of similarity solution we can think of for this particular problem. Okay. So we will start with the velocity scales, maybe I will go to the board to explain this. So in the y momentum equation, I will not erase this part because we will require this soon. You see, what is you see? Epsilon cube LC square rho g by mu UC, this is of the order of 1. So if you look into your notes, epsilon cube LC square rho g cos theta by mu UC is of the order of 1 for y momentum body force to be dictating the UC. from there we are getting this. So this means you have UC is of the order of mu by epsilon cube LC square rho g. Sorry, is the other way, right. UC is of the order of epsilon cube LC square rho g by mu. Now look at the expression for PS. I will try to get back to the slide. These equations are so I mean involved that it is better to use the slide to do it quickly. PS. So yes. So P minus, so PS, look at the equation number C in the right column. PS is equal to P atmosphere minus epsilon cube by capillary number into something plus the disjoining pressure contribution. So first assumption is we are neglecting the disjoining pressure contribution for this particular problem. Many research problems it is very important, I am telling you, but if you know how to do the algebra you can do it with the disjoining pressure term also. So that is not, that is just a mathematical exercise. So I am trying to demonstrate the mathematical exercise. The other term epsilon cube by capillary number that is what? So where from that term has come? Epsilon cube by capillary number sigma del 2 u del 2 h del x square, that has come from basically sigma the into 1 by r, the radius of curvature. So that is the surface tension term. Now how important that term is we will now assess. So what is the capillary number? Mu UC by sigma. So that is equal to mu epsilon cube LC square rho g by mu sigma, right. So this is epsilon cube rho g LC by sigma by LC, right. What is this? This is gravitational pressure, right, and this is the Laplace pressure due to surface tension. So this ratio, this is an indicator of the gravitational force by surface tension force, this is called as bond number, BO. So recall that in the Laplace pressure term we had a term epsilon cube by capillary number, right. So epsilon cube by capillary number is equal to 1 by bond number. So we will, so our assumption that Laplace pressure term is not important can be justified only if bond number is large, right. So we will assume that the bond number is large, that means epsilon cube by capillary number will be small. So if you look at this expression for A, if you look at this expression for A now, PS is equal to P atmosphere plus the Laplace term plus the disjoining pressure term. Laplace pressure term is negligible and the disjoining pressure we have already neglected. So this, for this present problem, for only this problem, right, do not generalize it, For only the example problem that we are working out now, this is P atmosphere. Okay. Now what are the other parameters for this problem? This is cos theta is 1 and sin theta is 0. Not only that, epsilon cube LC square rho g by mu UC, this is equal to 1, right. The reason is obvious, that is how we set the velocity scale. By looking into that body force only we set the velocity scale UC, so that will be 1. So based on this we will proceed further. Not only that, we will assume that there are no tangential gradients of surface tension. For example, you have not applied any temperature gradient so that it creates a surface tension gradient. So integral u0 dy between 0 to h is equal to a integral y square by 2 minus yh dy 0 to h. So this is a, this becomes h cube by 6 minus h cube by 2, so minus a h cube by 3, right. So it becomes del del t del h del t plus del del x of minus a h cube by 3 equal to 0. So del h del t is equal to del del x of h cube by 3 del h del x, right. This is our governing differential equation. What are the boundary conditions? At x equal to 0, what is at x equal to 0? Look at the diagram, let us go to the diagram. X equal to 0 in this diagram is what? Y axis. At x equal to 0, what should be the boundary condition? Del h del x should be equal to 0, right. This is because of symmetry. Gravity is not breaking the symmetry. So the droplet is spreading, maintaining the symmetry with respect to y axis. So at x equal to 0, del h del x equal to 0, and at x equal to L, which is a function of t, what will be it? H equal to 0. So this is our problem definition. We can now forget about the previous derivations. This is the equation that we want to solve. Now you assume H is equal to T to the power alpha into F eta, where eta is equal to some constant into x by t to the power beta. Question is why are we attempting to assume this form. Now if self similarity does not exist, then we will see that this form will not be satisfied. So there is not always a guarantee that this form will be satisfied. Now what it is saying? It is saying that h is varying with with t to the power an exponent. From your intuition, what will be this exponent? Positive, negative, 0? Yes. So how do you see, think about it? It is a very simple answer. With time, as t increases, what does happen to h? H decreases, so you expect a negative exponent, right? And this eta, see this is like, and when h decreases, L should increase. L is the horizontal footprint of the droplet, which is called the droplet radius. So if h decreases, L should increase, so L scales with t to the power beta, so we expect beta to be positive. So this is like x by L, which is like a similarity parameter. So whether this will be actually a similarity parameter or not, it depends on whether in the final simplified version of this governing differential equation this t will be eliminated. If this t is eliminated, it will be a function of a single variable eta which contains x by L. Okay. So we will see that whether the condition of getting a similarity solution may be satisfied, because this problem physically hints self similarity. Droplet radius, droplet height decreases, and in proportion the stretching the droplet footprint increases, right. So now let us treat that governing differential equation. So del h del t, we will do these terms very carefully. If I make any algebraic mistake, please correct me, I have forgotten to bring that notes with me, so I will do it in the board, but in case I make a mistake, you please let me know. So del h del t is equal to alpha t to the power alpha minus 1 f, I am just writing short, f means f eta, plus t to the power alpha df d eta into del eta del t, right. So this is alpha t to the power alpha minus 1 f plus t to the power alpha df d eta, df d eta we write f dash, shorthand notation, del eta del t, del eta del t is ax, this is basically t to the power minus beta, so minus beta t to the power minus beta minus 1, alright. So this is alpha t to the power alpha minus 1 f plus t to the power alpha f dash, ax means eta into t to the power beta, ax is eta into t to the power beta, so that t to the power beta and t to the power minus beta cancels, so minus beta into t to the power minus 1, just check this is alright. Then there is a relationship between alpha and beta. See, this similarity will hold with a constraint of volume conservation, right. The h decreases and the L will increase in consistency with that, that we can say from intuition, because volume of the droplet is conserved. If that is not conserved, you cannot tell anything about that. So volume of the droplet is conserved means integral h dx from x equal to 0 to x equal to L, that is constant. This is volume conservation. Right. So let us substitute integral of t to the power alpha f dx is t to the power beta by a d eta is equal to constant. Can you tell that the final result, should it be sensitively dependent on what constant we choose? Actually not, because the constant, because ultimately the prefactor in the solution will be scaled with this constant. So you can normalize this and you can choose this as 1, for example, not a must. I mean, whatever you choose, the final result will be scaled with that. Okay. So this integral, so eta 0 to, let us say, eta 0. What is eta 0? Eta 0 is eta when x equal to L. When x equal to L, the corresponding eta we call as eta 0. So t to the power alpha plus beta integral f d eta is equal to a. When will this result in a self similar deformation of the droplet? When there is no t variation, that means alpha plus beta is equal to 0. So beta is equal to minus alpha. Okay. So here in place of beta we will write minus alpha, so this will be alpha. So this is alpha t to the power alpha minus 1 f plus f dash eta.